So I grew up in Spain, as you just heard, and as a child, I spent a lot of time reading science fiction, a bit too much of science fiction, not enough science maybe. But I was fascinated by these stories, right? Because they told us about a future in which we would have traveled to the stars and we would have met alien species. And how cool is that, to find an alien species, something that you've never seen before? And these are stories that are not just fiction. I mean, in fact, we do spend a good amount of efforts and money in building telescopes that allow us to scan the galaxy, try to find signs of life, planets that could harbor life forms that we have not seen before. But what if instead of pointing our telescopes out there, we use them to look at a much closer place, our bodies? Well, if you did that, what you would find is that our bodies are in fact thriving with millions of very exotic life forms. We are, as you heard earlier this morning, we're actually more bacterial than human in a sense. And these organisms are playing very important roles in our well-being. They can produce certain vitamins that we cannot produce. They are able to ferment a dietary fiber. And so we've co-evolved for a large amount of time with organisms that help us in many of these functions. So perhaps it's not very surprising that alterations in these microbial communities can impact human health. A few years ago, we were part of this particular study that showed how if you look at twins that are discordant for obesity, the type of microbes you find in the obese twin and in the lean twin are actually very different. And that shows an association. But you can actually now say, well, what if we take those microbes, we put them in a mouse that has never before been exposed to microbes, so they were raised on sterile conditions, and then we give these mice high-fat diet. Well, what happens is that the mice that received the microbes from the obese twin is going to start gaining weight very quickly. It's going to start adding adiposity. So that's telling you that it's not just an association, it's actually a causation, at least in a mouse model. And we've seen this type of effects in a number of diseases, not just obesity. We've seen it on diabetes. We're seeing it on allergies. We're starting to see this even on behavioral disorders. 2 years ago, we were working with a group of neuroscientists. They had a mouse model of depression. A technician made a mistake and gave this very sad, well, this is a rat, it's not a mouse, but the technician gave the colony an antibiotic that was not supposed to be given to that particular colony. And so what we saw is that by giving antibiotics to the mice, you get rid of the microbes, but you get rid of the depressive behaviors. It was now a happy mice, a happy lab mice. And we thought, well, this is interesting. What if we do a small experiment where we now take a group of depressed mice and a group of happy mice, and we take the microbes from this guy and we put them over there? Well, what happens is that you actually get depressed mice. And so this is telling you two things. Again, this is telling you that there is a causation. It's also telling you that if you have happy mice, you should not send them to neuroscience labs. So we've seen this again and again on a number of diseases. As you heard this morning, the answer to all of my questions is going to be it's epigenetics or it's the microbiome. But why are we seeing this relation between altered microbes and a number of diseases that are becoming much more prevalent in developed countries, in Western countries? Well, we got some hints from some early studies we did on a bit unrelated research to obesity, diabetes, or any of these diseases that we mentioned. We were interested in looking at what type of microbes different populations would have. And so we were studying in particular group of US subjects, and a group of Yanomami Amerindians in the Amazon. Never before been in contact, essentially hunter-gatherers. The first time they are being in contact, we ask them for poop so we can look at their microbes. And so, you know, they happily produce for us. And what we found was that, you know, each of these populations harbor very different microbes. David has very different microbes than I have, and I have very different microbes that you have. And, but even within this variability, there's a huge separation between these two populations. And it's not just the type of microbes that we have, it's the diversity of microbes that we host. So Western populations tend to have a much lower diversity in the type of microbes that we have. And so we find that there's two extremes, right? High diversity, microbes that are very good at extracting energy from plant sources. And in our case, low diversity, and bacteria that are able to extract energy from protein much more efficiently. And the interesting thing is that as we start looking at more populations, we found an interesting pattern. We found a gradient whereby the farther away you go from an ancestral lifestyle, the less diversity you have. And the farther away you get, the more you're changing your plant-loving microbes for meat-loving microbes. So what exactly does this mean for us? What do we mean by westernization, by this process? Well, for one thing, diet is very different between these populations, right? I don't hunt for my food, and the Yanomamis don't go to Whole Foods very often. So we know that for the last few decades, there's been a radical change in what we eat. We tend to eat much more sugar than they do. There is a loss of seasonality. So next week, we'll all pretend that we like pumpkin pie and things like that. But you could have that anytime throughout the year. And that's not been the case for most of human history. Food used to be seasonal. And this change is actually happening from very early on in life. So in Western countries, you can breastfeed, of course, but you have access to formula. We have access, children in Western countries have access to sugar much earlier than in traditional lifestyles. So all of this is naturally affecting the type of microbes that we're hosting. Now there is a second component to this, which is medication in general, but antibiotics in particular. So I think it's very clear that antibiotics are incredible drugs. They save millions of lives. We get to live to 80, 90 because of antibiotics mostly. But it's also true that we're overusing them, and particularly so in early life again. By the age of 2, the average US child will have had 3 rounds of antibiotics at least. And 3 rounds is exactly the amount that you need to have a higher risk for developing obesity later in life. And so our hypothesis is that this is mediated by changes in the microbes. And the third factor here, something that is often overlooked, is delivery mode. So we now routinely perform C-sections, which, again, are life-saving procedures, both for the mom and for the child. But while the World Health Organization recommends 10 to 15% C-sections, most Western countries are now well above that number. The US is 30%. We're talking last night over dinner. Mexico is 50. Some places in Brazil are closer to 90% C-sections. And so because the baby is not exposed to the bacteria that you have in the birth canal, you start life with a very different first bacterial impression. And so what do we do about this? Well, we've been exploring 3 approaches to try to re-engineer the microbiome. We're going to try to go back from this altered microbial compositions to something that is what we probably used to have in ancestral societies, ancestral lifestyle. The first approach that we've tried is this idea that is now often called vaginal seeding. So this is a procedure that we pioneered with my colleague and good friend Margarita Dominguez, who Rutgers did a fantastic job at bringing here. As I just told you, delivery mode affects the type of microbes that a baby gets exposed to, right? Because a C-section baby does not come through the birth canal, and so the first microbes you get are essentially environmental microbes, microbes from the maternal skin. And so this sets the infant in a very different path in terms of its immune development and in terms of the bacteria that are going to colonize the baby. So what we've been doing is this vaginal seeding procedure, which essentially consists on swabbing the infant as soon as it's delivered with a gauze that is soaked on a vaginal fluid. Surely enough, this does not recapture exactly what the natural delivery is. There is stress, there is hormones, like all of those things are clearly missing in this group, but at least we can demonstrate that we can bring back some of the bacteria that a C-section baby would otherwise have not been exposed to. And so as a result of some of these studies that we did a couple of years ago, now there's a number of trials that are looking at whether this procedure can be sufficient to lower the risk of obesity later in life, to lower the risk of developing food allergies. So this is one aspect that we've been studying. But what if, your baby was delivered vaginally, was exposed to these microbes, and still there is a need for intervening somehow, of reshaping bacterial communities? Well, the second type of approach that we've been looking at is diet. Can we modulate, can we control bacterial communities by playing around with diet? And as any nutritionist and dietitian in the room knows, diet is a very simple thing. You have good food and bad food, lots of the first, not many of the latter. We found out very early on that the type of interventions that we were doing with diet were very crude. And so the way we've approached this problem is we think of diet as this panel, where you have multiple knobs, and we're going to try to move one knob at a time and see what effect that has on bacterial content, but also on phenotype. The idea being, maybe we can find what combinations of different nutrients in diet change the microbes in the way that you want it for a particular phenotype to be observed. And so what we found is that you can actually do that, at least, again, on mouse models. In particular, what I'm showing you here is how modifying slightly the amount of psyllium in a particular diet that we're using can result in very different outcomes. So you don't need to revamp completely the diet. You don't need to switch from a high-fat to a low-fat diet. Maybe understanding what nutrients have the maximum effect size in your outcomes can be sufficient. And so we think this is a very powerful tool if we can now translate this into human studies. Finally, the third approach we've been thinking about is, there are cases where your microbiome is going to look a bit like this, right? It's completely devastated. Changing the fertilizer is not going to bring it back. And so what do we do in these cases? And the approach that we've been exploring is fecal microbiota transplants, the idea of completely restoring your microbes. It's a very simple idea. Basically, you find a healthy donor who has no pathogens, who has no gastrointestinal disorders. We screen them for a number of conditions, and you come up with a slurry that you then infuse into the patient through a colonoscopy. So this is my colleague Ari Greenspan on his hazmat suit performing this procedure. And so we've been interested in questions about how efficient this procedure can be to restore diversity, to bring back your microbiome to a point where you do see a phenotypic outcome later on. And so we are actually finding that this is actually possible to do in particular conditions. So in Clostridium difficile infections, we can bring back diversity very quickly after the transplant, and this is maintained over a period of months. So now one of the things that we're starting to explore is how do we move from these type of colonoscopy-based approaches to fecal transplants with pills, right? So this would simplify the logistics, make things, make the economics of this approach much more feasible. So, so I think these are the approaches that we've been studying. I think we are at a crucial point in our studies because I'm telling you that microbes are associated with disease, microbes cause disease, and I'm telling you that we have the tools to restore those microbes. But the truth is, or at least I feel the truth is, that our restoration efforts are perhaps a bit crude. We're not quite achieving what we want. We are transplanting whole communities, right? We can't go around smearing babies with vaginal fluids or passing stool from a donor to a patient. We need to understand better what those communities are composed of. I think there needs to be a push for defined communities where you know exactly what are you putting in what quantities, and through which mechanisms do you think you are restoring health. So I think at least what I want to do is something much more similar to this. So this is the Adoration of the Shepherds, and it took 10 years to restore this painting. But look at the result. So wouldn't it be beautiful if we could do the same for your microbes? Thank you very much.